This was originally supposed to be one unusual seminar in that I'm not talking about my own research or even something I'm an expert in. I'm talking about something I'm an interested amateur in. And this talk came about by the suggestion of Christian. He floated the idea that I should give a cake seminar on interpretations of quantum mechanics, inspired by a really lovely seminar, theory seminar, not cake seminar, given a few months ago by Jacob Berendis. This was supposed to be one unusual seminar, but last week we got so much engagement that I went wildly over time, and I have now the unusual distinction of, I think, giving the first two-part seminar in cake seminar history. Thank you all who decided to come back, and I see a few new faces as well. So I will attempt a quick recap, hopefully not an hour recap of the hour seminar. So the idea behind this is that we have this excellent theory, quantum mechanics, that underlies basically every modern physics model that we use. All of hadron physics relies on an elaboration upon quantum mechanics, quantum field theory, quantum optics, quantum computing, condensed matter physics. They all rely on quantum mechanics, and we know that it's true to tremendous precision. But there is an apparent fundamental vagueness in the way that it is formulated. The axioms of the theory involve statements about things that you can measure, and the way that measurement is typically thought of requires dividing the world into the quantum system that you describe using the Hilbert space formalism, and a classical world that you do not describe using the Hilbert space formalism, but classical physics instead. It is unclear where this cut should be placed, and it is unclear why you should need two incommensurable theories of physics in order to describe the world. So interpretations of quantum mechanics come about as an attempt to solve the measurement problem, to have a single self-consistent description of the world that doesn't divide it into a part that's described by quantum mechanics and another part that's not. I will be going over, or the intent was to go over, 3 example interpretations. Pilot wave theory is an example of a hidden variable theory in which you assume a classical-like description is valid at all stages. The relative state formulation, which I'll start on today, since I finished the pilot wave part last week, and informational interpretations, which are a little bit more radical than the first 2 class of interpretations. And I'll discuss QBism as an example of it. I'll elaborate on what informational interpretation means when I get to it. I also want to reiterate that unlike a lot of other areas in science, we are not even close to a consensus on it. Although the Copenhagen interpretation, which isn't entirely self-consistent because it does require this division of the world into a quantum and classical part, even though it's the most popular, it doesn't even have 50% support among physicists, and the majority of those who do have it as their favorite interpretation aren't even confident in it. And there's a whole mess of other interpretations. So this is really a controversial area. I went through hidden variable theories, which I'm not going to reiterate. And today I'm going to start discussing the relative state formulation of quantum mechanics. The relative state formulation kind of goes in the opposite direction of hidden variables theories. Instead of assuming some sort of classical reality underlying quantum mechanics, we assume that the Hilbert space formalism, the description in terms of state vectors or wave functions that evolve by unitary Schrodinger evolution, applies to the entire universe, and that's all you're going to describe it. So you do quantum mechanics with only a wave function without a classical description of a measurement apparatus. Measurement is then supposed to just be another physical process. And a very schematic description of what happens is, if you are performing some sort of interaction that's supposed to measure an observable A, so A hat operator, with eigenvalue an. Actually, that shouldn't have a subscript there. A hat operator with eigenvalue an. A general wave function can be decomposed into a sum of eigenstates. Then you have a state of your system, state of some other physical system, which is your measurement apparatus. It starts in what we call the ready state, and it's typically written with the subscript 0, and you perform some sort of interaction that entangles the state of the system you're interested in and the measuring apparatus. So that after the interaction is concluded, at least to a very good approximation, you can write the joint wave function as a sum over tensor products of some sort of measurement reading corresponding to the eigenvalue of the observable you're measuring and the eigenstate. And the relative state formulation says that actual wave function of the joint system has all these components, but somehow live inside the wave function in one of these terms. So a little bit of a silly illustration of this. Say you have a photon in some linear diagonal polarization state, so horizontal polarization plus vertical polarization. Peter, the cat, wants to measure it. So he passes the photon through a polarization filter. If it's vertically polarized, then it's blocked by the filter. Nothing happens. He gets bored. He falls asleep. If it's horizontally polarized, it passes through the filter, hits some sort of trigger, creates some sort of light show. He gets really excited. So you go from a tensor product of some superposition of horizontal and vertical polarization in your quantum system and ready state for your measurement apparatus to an entangled state of one particular outcome, horizontal polarization, plus one particular detector reading, excited, happy Peter, versus vertical polarization and bored, asleep Peter. So the wave function in general contains all possible outcomes, and you could perhaps think of it as the wave function contains different worlds in which these different measurement outcomes happen. The relative state formulation is sometimes called the many worlds interpretation for this reason. So you might imagine that each of the terms in, say, this wave function with perhaps even infinitely many different outcomes exists in some way. But it's kind of a myth that this involves a literal splitting of the universe into worlds every time a measurement happens. All you have is unitary evolution of the wave function. You don't have a mechanism in which worlds are being generated as distinct entities in the theory. The worlds are just an effective description of how things look from living in one of the pieces of the wave function. So why would we do quantum mechanics this way? Similar to the hidden variables formulations, the desire is to have a single description of the worlds that applies at all times, whether measurement is happening or not, whether it's a microscopic or macroscopic system. So you don't have this shifty Heisenberg cut. Another reason that people really like this interpretation is parsing. Whereas in the hidden variables formulation, you need to posit some additional hidden variables outside of the quantum mechanical formalism. With the relative state formulation, you assume that all that exists are your states in Hilbert space that evolve by the Schrodinger equation, something that's there in quantum mechanics anyway. So very silly illustration. I don't have a classical side. There's no Heisenberg cut. The wave function is king in this interpretation. There are some conceptual difficulties with this formulation, and there's a reason it's not universally accepted. One of the biggest ones is this controversial how or whether probabilities can arise in the relative state formulation, which is pretty important since probabilities are a central aspect of how we test quantum mechanical theories. Even when we're doing scattering experiments, ultimately we end up using the Born rule and calculating scattering rates. We need probabilities. One of the things that can be ruled out right away is that counting worlds doesn't really make sense. You can't really use a frequentist approach to probability in the relative state formulation because it doesn't actually correspond to a literal splitting of worlds. In fact, if you did try to take this seriously, that it's a literal splitting of worlds, you would get the wrong probabilities. If you had a wave function that was, say, square root of 2/3 times one thing plus square root of 1/3 times another, you have two worlds, but the probabilities will be 2/3 and 1/3, not half and half. So counting worlds doesn't make sense. So approaches to try to formulate probability in the relative state formulation tend to rely on some sort of subjective probabilities, usually Bayesian probabilities. There are multiple different approaches to it. Some of them are epistemic. There's this principle of self-locating uncertainty. I'm not sure offhand if Sebbins and Carroll came up with the idea of self-locating uncertainty or they built on the idea, but one of the most famous papers using this idea of self-locating uncertainty is by Sebbins and Carroll. Same Sean Carroll who wrote that great general relativity book. So the idea with self-locating uncertainty is you live in one of these pieces of the wave function. How do you judge in an epistemic way, in a knowledge or ignorance way, what's the likelihood that I am in a particular branch? So that's what's meant by self-locating uncertainty. Many other proofs, including the earliest proofs by David Deutsch, for instance, are decision theoretic. So they're not so much to do with what you know, but how you should act. They're usually based on things like betting odds and Dutch book arguments. I'll discuss Dutch book arguments a bit more in the next section on QBism. Either way, probability is about some sort of degree of belief. It's attached to an agent living somewhere inside the wave function, so it is subjective. A lot of these proofs are not so much mathematical as they are conceptual, so it's kind of difficult to gauge whether they're valid in a formal way, and there's a lot of controversy. Some people accept them, a lot of other people don't. So there's no consensus about whether the Born rule can be derived or has been derived in the relative state formulation. Yes.
Before we get to the example, some of the conceptual problems that arise in this interpretation of quantum mechanics you also have in the very concept of probability. Isn't it that concept of probability inherently assumes that you look at a subsystem of a much larger system, and that there's a large, so to speak, dynamics or so, or motion that you do not control. You only control part of that, and you interpret that as a probability. So I think some of these questions are really very general and concern the very notion of probability. I mean, they're more general than quantum mechanics.
Yeah, that actually is an issue that is run into in a lot of the interpretations. They do run into the question of what exactly do we even mean by probability? And that's actually something that is discussed by Sebbins and Carroll in their paper. So I actually don't remember what they say about this, but have you heard of the Sleeping Beauty problem? So it's this kind of another unsolved puzzle in probability that has nothing to do with quantum mechanics, but is very much related to their idea of self-locating uncertainty. So there's a Sleeping Beauty. I'm going to forget the exact way it's formulated, but it's along the lines of there's a woman who's asleep and she wakes up and a coin is flipped. If it's heads, her memory is erased and she goes back to sleep. If it's tails, her memory is not erased. And then she's woken up again on the next day and the coin is flipped and it's heads or tails. Is the probability that she sees tails 1/2 or the probability she sees heads 1/3 or 1/2? Something along those lines. And they come to an answer about this based on their principle of self-locating uncertainty. I forget what their answer is. But apparently that's considered an unsolved problem in probability theory, having nothing to do with quantum mechanics. But yeah, you're right that this does touch on open conceptual problems. And the next interpretation I cover, QBism, will also on it as well.
Also about this, can one get a notion of probability by tracing out the part of the wave function that refers to the measuring apparatus or the larger world? Or so, I mean, is there a...
That is a little bit tricky because that could potentially be circular. The idea of tracing out kind of assumes you already, that tracing does correspond to a probability measure in some sense.
I mean, Adam, you said that it corresponds to not a many worlds point, but a unitary evolution, right?
Yeah.
And that to me always, unitary to me means probability conserving, right?
Well,
Is that not
the
case?
unitarity is there whether you have the probability interpretation or not. You have a function that maps time onto a vector in Hilbert space, and operator that evolves in time is unitary in the sense that the inverse is its adjoint. So it's just a mathematical thing. Once you do have a probability interpretation, unitarity implies the conservation of probability. But it's a mathematical property of the Hilbert space formalism, whether you have the probability interpretation or not.
But there's a question online. Gabriel? You can say something now.
Hey, I just wanted to maybe make a remark here. The issue with probabilities that Adam's trying to highlight for the many worlds interpretation is, where does the idea of probability enter this picture in the first place? In the hidden variables case, you had an uncertainty in the initial conditions for all your trajectories. In the many worlds case, you just deterministically get every outcome as a part of the wave function. So there's no reason to say that there should be an uncertainty there. The probability of every outcome happening is 1. So it's kind of separate from the issues of what is a probability. How do you calculate probabilities? You have to get probabilities into the game in the first place.
Yes, exactly. And the idea with from Sebens and Carroll with the self-locating uncertainty is every outcome does happen, but you don't see every outcome because you're only in only one of the possible outcomes. Which one are you in? So it's about where you are, not about what's happening. That's the self-locating. Yes.
So I wasn't there in your last talk, but just to make sure, all these interpretations already assume that quantum mechanics is complete.
Yes.
And okay, so that was my first point. And how do these interpretations answer the questions like the EPR paradox and the Wigner-Friends paradox and all that?
So they answer it in different ways. The next slide with the relative state one I'm going to get in, I don't call it the EPR paradox, but it's an elaboration on the EPR paradox by Merman and others, the GHZ experiment.
Okay.
Is that okay to move on? Sure. Would you say? So the EPR paradox is a interesting part. We covered it a little bit last time with regards to pilot wave theory. I didn't call it the EPR paradox, but it was effectively that. And it has to do with the contextuality or non-locality in quantum mechanics. So the relative state formulation is widely believed, especially by its proponents, but even by some of its opponents, to be local. And this appears to contradict what we saw last week in the pilot wave formulation, in which you had this contextuality that implied non-locality in quantum mechanics. But the reason that this is consistent with locality is because the probability assignments and moreover eigenvalue assignments for operators are subjective. They're attached to someone living inside the wave function. And I'm going to elaborate on this with the GHZ setup. The GHG state is one in which you have three entangled particles, each of which is a two-state system. So all three of them pointing up versus all three pointing down. And it's a simultaneous eigenstate of all of these four non-local operators. First of all, in the fundamental ontology of the relative state formulation, you just have a wave function that's evolving by unitary evolution, by the Schrodinger equation. Unitary evolution is local by cluster decomposition. The Hamiltonian operator on two different places at space-like separation, two different places in space at the same time. They commute with each other. So unitary evolution is local. Next, the probability assignments and even the eigenvalue assignments are subjective because they're attached to an agent living somewhere inside of the wave function. So for instance, if Alice at one of these three detectors detecting one of the three particles sent in different directions is to measure the X projection of her particle's spin, then she doesn't know whether multiplying the projections that Peter the cat and Bob the builder measure will give her +1 or -1, because she doesn't know whether they both measure the Y projection or both measure the X projection. It's not until she communicates with them classically, which requires a signal that is limited by the speed of light, that she knows what they measured and thus what the outcome will be.
You just said something about the theory being local, and you refer to the Hamiltonian. I mean, in ordinary quantum mechanics, the Hamiltonian is not a function of space, or it doesn't depend explicitly on space. I mean, it's
an integral over a Hamiltonian density, which does evolve, which does depend on space.
That's like an extra concept.
But the Hamiltonian acting on two systems that are space-like separated, those Hamiltonians will commute.
Yeah.
I stated what I meant a little bit poorly, but that's what I meant to say. All right. Now, there is another conceptual problem with the relative state formulation, one that I believe has a solution, but a lot of other people don't, so I should touch on it. But it does get into some important properties of quantum mechanics as a whole that's interpretation independent. Formally, there's no unique basis for entangled states. You take something like this Bell state, two particles spin up, two particles spin down, relative positive phase. Well, you can also write it in this form. You can add and subtract the down, up, and up, down. And you can note that, well, up plus down is going to be right, and up minus down is going to be left. And you can write this as, well, a superposition between both going right, both having spin projection along the right and both having spin projection along the left. If we were to look at the two-state example from a few slides ago, where Peter can either be awake because he measured horizontal polarization or asleep because he measured vertical polarization, you could do something similar here. You can say, well, why do we see states where Peter is awake and asleep, but not coherent superpositions of both of them? So we live in the wave function, but we experience a particular basis of it. And the relative state formulation needs to answer why we experience particular bases in which, say, a cat is awake or a cat is asleep, and not other bases that are equally valid at a basic level, such as coherent superpositions between them. However, a possible answer, one I believe works, some people think it doesn't, is found in environmentally induced decoherence. So in any actual experiment, there's going to be a third system always involved, the environment. The environment interacts with your measurement apparatus. You have air molecules bouncing off it. You have photons bouncing off it. It interacts gravitationally with the Earth, all of these things. The environment apparatus Hamiltonian is also going to be diagonal in certain states. The idea here is that environmental perturbations will scramble the phases of these states, but won't turn them into other states. So for instance, you have a state where Christian is chuckling and winking, and a state where he's not. And in principle, coherent superpositions of these exist, but scattering of air molecules off of Christian doesn't cause one to transition into the other. Scattering of air molecules off of Peter the cat don't cause him to flip from being awake to being asleep and vice versa. You have particular states that are stable against environmental perturbations up to a possible scrambling of the phase. And the scrambling of the phase makes coherent superpositions of these states unstable against environmental perturbations. So an example in this excellent paper by Wojciech Zurek is this. I did have a worked example I would go through, but for want of time, I'm going to skip it. Now, it is controversial whether this idea of environmentally induced decoherence, which does set up a preferred basis for macroscopic systems, states that are stable against environmental perturbations, whether it helps the relative state formulation. Because if you have a wave function for the universe as a whole, the universe as a whole doesn't have an external environment. But when we talk about our experiences as beings living inside the wave function, using particular measurement apparatuses to measure properties of quantum systems, well, from our point of view, there always is an environment that we're going to be entangled with. So I have worked examples from Zurek's excellent paper that I'm going to skip for the sake of time. I will mention that there are some related interpretations that aren't quite the same as relative state, but share some properties and not others with them. One of the ones that's fairly popular is called consistent histories. Consistent histories is very much inspired by decoherence-based arguments. You basically write out the set of all possible histories that are consistent with environmentally induced decoherence that are capable of reading records, and you can figure out probabilities for each of these histories occurring. We only see and remember one of the histories, and the formulation is agnostic as to whether the other histories actually occur or not. Another one, Carlo Rovelli is responsible for this, is called relational quantum mechanics. Like the relative state formulation, it talks about states existing relative to us, but unlike the relative state formulation, it doesn't assume that there's a true wave function of the universe we're living inside. So it more or less says that the Hilbert space formulation only makes sense from the perspective of some sort of observer. And I'll actually get into something kind of similar to that with QBism in the next part of the talk. The last one I should mention for completeness, but I am a little bit confused by it. It's David Albert's many minds interpretation. Just like with the relative state formulation, you assume that there's a wave function evolving unitarily and that we live inside of it. But we only see things from inside the wave function. And the reason that we see particular configurations, that we have a preferred basis, is that this is the basis that corresponds to conscious experience. Aside from kind of getting a little bit philosophical with talking about conscious experience, I don't see how it's that much different than the relative state formulation personally, but a lot of philosophers consider it a distinct interpretation. Do we have more questions before I go on to informational interpretations? All right. Now for the last part of the talk. The last set of interpretations are actually the most popular ones aside from the Copenhagen interpretation right now. And they're especially popular among people doing quantum information and quantum computing these days. So what are the informational interpretations? Instead of having a Heisenberg cut between a quantum system that is described by Hilbert space that has a state in it that has a wave function, the wave function evolves by the Schrödinger equation, you actually don't have anything on the objective side of the cut. you have an information gathering agent, that's you or me, who uses the Hilbert space formulation to describe what they know or they believe about a system. The wave function is used to encode this knowledge or belief, and the Schrodinger equation is used as a personal tool by this information gathering agent in order to update their knowledge or beliefs. Collapse rule is used because you get new knowledge. So you avoid the Heisenberg cut between the information gathering agent and the system by strategically not saying anything about the objective state of affairs of the system at all. You only have your subjective knowledge, and of course you apply a collapse rule or a update of your probability distributions when you get new information, when you have new beliefs. There's nothing contradictory about that. But the entire formalism of quantum mechanics, or at least the probability part of it, is just a formalism for informing your knowledge or your beliefs. So QBism is an example of a radically subjectivist view of quantum mechanics. It was originally short for quantum Bayesianism, but it's now considered a little bit distinct from Bayesianism per se. Bayesianism is a component of it, but it's not all Bayesianism. The wave functions encode subjective degrees of belief, and that means that there isn't a right wave function as well. They're not objective properties of the system in particular. And one of the peculiar things about this formulation is that the Born rule is normative. The Born rule tells you what probabilities you should assign. It doesn't tell you what the system is actually doing, and it doesn't tell you what you're doing. It just says this is the probability rule you should use. Schrodinger's equation also tells you how you should update your probability estimates, how you should upgrade your beliefs. And the collapse postulate says how you should update your state. It doesn't tell you about what's actually going on. And of course, doesn't tell you what you do believe, but it tells you what you should. Probability in general is normative. And that's a little bit peculiar. It's a little bit different than the frequentist approach of counting states. But the idea behind it is they describe how we should behave. And the operational definition that QBists use is in terms of hypothetical gambling scenarios. The underlying maxim could be, don't fall for a Dutch book scam. And I did promise previously that I would talk about what that means. So a Dutch book is a set of probabilities for possible outcomes and payouts for those outcomes if you were to buy into a set of odds and outcomes designed so that you are guaranteed to lose money no matter the outcome. You can actually derive a lot of the standard rules of probability, even things like that the probability is bounded by 0 and 1 from this maxim. And I will give you a couple examples. First one, that the probability has to be between 0 and 1. So say a bookie wants to sell you a bet that an exotic glue ball will be measured with probability P and hole D at some point. Well, you have a payout X if the glue ball measurement happens. And because the probability is P, that means you're paying X times P for the possible payout. The net payout results are going to be X, if you get it, minus P times X, because that's what you paid in, and minus P times X if it's not measured. So if you assume that the probability is less than 0, or X times P to be positive, X has to be negative as well. Well, you'll get a negative payout if it happens, and of course you paid in either way, so you're going to lose money regardless of the outcome if you assume probabilities can be negative. If you assume that P is greater than 1, well, it's positive, so X is going to be positive too. You're paying in a positive amount. And well, 1 minus P will be negative, negative XP will be negative. If you assume that if you use a probability that is not between 0 and 1, a bookie can scam you by selling you possible payouts that will lose money. Pretty simple. A little bit more of an involved but still pretty simple example is given in this really excellent paper by Caves, Fuchs, and Schock of if you have two mutually exclusive outcomes, say one of them is that the first EIC physics events happen in 2031, and another is that the first EIC physics events happen in 2032. Then the probabilities for each of them the probability that one or the other should happen should be the sum of the probabilities. That's a basic rule of probability, but if you assume that it's not true, then a bookie could sell you a collection of possible payouts that would lose you money regardless of which of these two happens or if neither happens. The only way that they can never sell you a Dutch book is if the determinant of this matrix is 0, and therefore the probability of either outcome is the sum of the probabilities of each. So kind of the upshot of this is that it is possible to derive all of the mathematics of probability theory, even going as far as deriving Bayes' rule for how you should upgrade beliefs, based off of simple maxims about don't fall for scams. So a few other things about QBism that are kind of worth elaborating on. The state is not objective. It's not an actual physical property of the system in QBism, but that doesn't really contradict quantum mechanics and how we use it. The state vector is not actually an observable. There's no protocol that you can use to determine the state of an individual system. Is the system in psi or is it in some non-orthogonal state? You can't do a single measurement to determine that. You can determine that it's not in any, you can distinguish between a state and an orthogonal state perhaps, but not orthogonal state. In fact, the no cloning theorem precludes determining in a single shot measurement an unknown quantum state. If you could, then you could set up a Bell state, entangle the two particles, send them to two different locations, and then Bob could create a bunch of clones of one of them, and then destructively measure his state, but have clones of it and use that to communicate with Alice. You could communicate faster than light, it's not true. So the state of a system is not measured in a single shot measurement. It's not unobservable. It's not analogous to the energy or spin projection or anything like that. It's inferred either by theoretical calculation, you know what the interaction is, you know how to solve the Schrodinger equation, or tomographic imaging of an ensemble of identically prepared or similarly prepared systems. So QBism emphasizes the subjective nature of these inferences. You have a theory that you have very good reason to believe is true, and you use this to infer, you use this to inform, not infer, inform how you assign a state to the system. Or you have a procedure that you have very good reason to believe prepares similar or identical states. And you do repeated measurements on it through quantum state tomography, and you use what you measure to inform how you should assign a state to the system. And from the perspective of QBism, this says something about what we're doing in our field. When we talk about our femtoscopic, femtographic proton images, our PDFs, our GPDs, our impact parameter distributions, we're not taking a photo of a proton. That's not what an individual proton looks like. These are ensemble averages, but they're kind of subjective assignments. Now, one of the really peculiar things that is kind of the main reason a lot of people are queasy about QBism is that it seems like it's non-realist. It seems to be denying the existence of a real world. But this is a little bit of a misreading of QBism, one that I think is to some extent, well, kind of inevitable based off of the way that it's talked about. But it is, in fact, at least its advocates claim that it's a realist interpretation. Something that's worth remembering is that probabilities are not the only thing in quantum mechanics. The entire operator algebra The spectra of observables, current algebra, commutation relations, all of that are a really important part of doing quantum mechanics. Moreover, there are rules in quantum mechanics that QBism would claim are normative. So they're telling you something about the structure of the world because there are rules for how you should update probabilities, including the Schrodinger equation and including the Born rule. The states themselves might be subjective, but there's some sort of objective real structure to the world that forces you to use a particular mathematical apparatus to inform your beliefs. So the way that Chris Fuchs frames it is QBism is participatory realism. And I think that this has some analogs to what philosophers call structural realism, where you don't talk about the entities, the wave functions, for instance, as being the real things, but the mathematical structure of the theory describing something about the real world. There are other epistemic or information-based approaches out there besides just QBism. Most of those I don't really understand, so I can't comment on them, but it is worth pointing out that some of the earlier interpretations, such as the ensemble interpretation and the Copenhagen interpretation, are also largely based off of subjective belief or knowledge. So I actually managed to make it through the rest of the talk today, probably because of less discussion, possibly because of Russian too. Well, to summarize, the measurement problem is kind of the main outstanding problem with the Copenhagen interpretation. The Copenhagen interpretation tells you that classical concepts in classical physics are necessary to describe experiments, and this creates a divide between the quantum and classical world that is vague, not really well defined within the theory. Interpretations of quantum mechanics other than the Copenhagen interpretation are meant to get rid of this vagueness, and they all do so in different ways. Hidden variables theories, like pilot wave theory, are meant to get rid of the divide by assuming that a classical-like reality with exact configurations underlies quantum mechanics. The relative state formulation kind of goes in the opposite direction by assuming the Hilbert space formulation is always valid for both microscopic and macroscopic systems, and attempts to derive what we see on a macroscopic scale as emerging from the quantum formalism in some way. And then information-based interpretations such as QBism try to center the observer and take seriously the idea of a subject, of an I or a you, being part of the theory at all times. So it also, like the relative state formulation, uses Hilbert space descriptions at all times. But now the Hilbert space description is a subjective description attached to an agent rather than being a description of how things really are in the physical world. I skipped dozens of interpretations besides these. Some of them fall into these classes or similar, and some of them are actually quite different, such as spontaneous collapse theories or retrocausal theories, which are more likely to actually make different predictions from quantum mechanics, and they're kind of the main reason these are less popular. I do want to re-emphasize that there is a lack of consensus. There's no interpretation with more than 50% support. And the most popular one, the Copenhagen interpretation, most of the people who have as a preferred interpretation are not confident in it. And I feel like this XKCD here applies as much to interpretations of quantum mechanics as it does to standards. People seem to be frequently coming up with new interpretations to try to dispel all the problems and paradoxes that people don't like about the other interpretations, but then you just end up having yet another interpretation. One thing that I think is worth looking at is the commonalities that these interpretations have. They are, after all interpretations of quantum mechanics, which we know is true and we know describes the world we live in. Most observables also supervene on the context in some way in these interpretations. How they do varies between the interpretation, but a spin projection is not something that exists outside of an experimental context in any of these interpretations, including the hidden variables ones. There are some interpretations like pilot wave and the relative state, in which the wave function is an objective fact of the universe. That's not the case with QBism, so we're here outside this circle. And measurement is a physical process described by the evolution of the wave function in these two interpretations. However, something that the relative state and the QBist approaches have in common as well, because they both apply the Hilbert space calculus at all times, observables and probabilities are subjective and physics is local, whereas in the pilot wave formulation, physics is nominal. All of the interpretations teach us something about quantum mechanics, and a lot of the really interesting results that we've discovered the past 70 years, such as entanglement, secure communications protocols, quantum teleportation, the non-cloning theorem, all these things popped up in the context of people trying to understand what quantum mechanics is telling us about the world. Quantum computation was discovered by David Deutsch within the context of thinking about many worlds and doing computations in the different worlds in parallel. Bell's theorem was discovered in the context of the pilot wave formulation. He was interested in whether quantum mechanics had to be non-local as pilot wave theory. Anyway, that's what I had to say. Thank you for your time. And I'm open to more questions and comments.
Yeah, that's really good. Excellent. I was wondering about the femtography example of taking, it's not a photograph, right? Where do you say it?
Yeah.
They're not photographs, but they're on some languages. So when we do lattice calculations, right, we get photographs, and the more photographs we take, the more information we get about the distribution in a.
The results you present in the end, though, are averages over all the possible configurations.
They are, absolutely.
But you do have individual configurations.
Yes. So is that what you're saying here? In fact, is this an example of that?
Instead of ensemble average, I should have said something like composite images rather than single shot photos. That makes sense? I guess another thing to think about when people do these heavy ion collisions and they talk about initial state fluctuations, what they see the proton apparently looking at least in the context of these experiments, is the proton or the ion is not spherically or azimuthally symmetric. In each shot, it appears to be clustering in different ways. And that influences the way that the quark gluon plasma generates, moves out. It influences the, these not elliptical, but general moments for the triangle and all these other shapes. Can't remember the term.
Just a follow-up comment on that one. So this is the, if we consider it to be an ensemble, that's the question that was there in 1925 and like during those conferences between Einstein and Bohr. That is the question that they were tackling.
Yeah.
Whether quantum mechanics is a theory of the ensembles or a wave function describes one particular particle at that time. I don't know how this adds up onto that in any shape or manner. In that sense.
Yeah. So this is probably a place where ensemble average is not the right word to use in this context, because in the QBist view, you can talk about a single system using a wave function, but the wave function is not a property of the system. It's a property of your beliefs about the system. And your beliefs about the system can be influenced by an ensemble of similarly prepared systems. But it's still something that you use to describe what you believe about the individual system.
Good question.
Oh, yeah.
So you sort of rushed over the decoherence part a little bit.
Yeah, I did.
And you also had this calculation that you didn't feel like you had time to go through. Is that related to the decoherence?
Yeah, so it's a very, very simple example stolen from one of Wojciech Zurek's papers. Very excellent papers, and decoherence is a property of quantum mechanics independent of interpretation, so very much worth reading. But going through simple examples like this are a pretty nice illustration for how the argument works. In this example, you have three systems here. You have a okay, this is your Hamiltonian. You have your system that you're interested in, microscopic system. This is the environment apparatus interaction, so it doesn't affect the microscopic system, but it causes the environment and the apparatus to interact in some way. The apparatus starts in some particular state. It interacts with your microscopic state. So now your initial state after the measurement is your apparatus and your microscopic system are entangled. So say you're doing a spin Z projection measurement, so you get both up or both down, and your environment starts in some unknown and uncontrollable state, but say for the sake of argument, it's this alpha. After a certain amount of time, your state will evolve with this, the state of the tripartite system will evolve by unitary evolution. This will be the unitary operator that you act on it with, and the evolved state will look like this. So you'll have a tripartite entanglement between the microscopic system, the apparatus, and the environment. This hypothetical environment is only a two-state system, so it is a little bit cartoonish, but at certain times, and this is going to be periodic, your density matrix, if you trace out the environment, which is something you don't know and can't control, will be diagonal in the states in which your measurement apparatus is correlated with the microscopic system's property. And the off-diagonal components vanish at these integer multiples of some particular time. And of course, it will oscillate back into not being diagonal, and then it'll be diagonal again. But this is for a two-state system. If you have an environment with 10 to the 23 particles in it, and the exact phases that they induce to the pointer states are randomized, then the recurrence time of the diagonalization disappearing is going to be extremely long.
So the environment had a structure, and so did the measurement apparatus. I was wondering what that structure represents.
So the idea behind this, the particular example actually did with minus sign, but in general, you'll have randomized phases here. The idea is that you have particular states that are stable against environmental perturbations up to a scrambling of the phase of the wave function. So this is something like, for instance, if you have a particle on this side of the room and a particle on this other side of the room, you can have coherent superpositions between them because those exist in your Hilbert space. But your environment isn't going to induce a particle here to disappear and reappear over there and vice versa. So particles being in either of these locations are stable against interactions with the environment. The coherent superpositions are not, because the interactions are going to randomly scramble the phases of these two pointer states. So any coherent superposition, well, the relative phase of the two parts of the superposition are going to randomly change, and the coherent superpositions are not stable. So that's supposed to be the idea behind it. But the bigger your environment is, the more it scrambles the phases, and the more stable the pointer states become, and the less stable coherent superpositions become, which is a good thing if you want to show that there's a preferred basis for what you'll actually see, and a bad thing if you want to build a large quantum computer, because it will destroy your coherence.
I don't see any more questions, so let's thank Adam again.